and welcome to another Common Core Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and today we're going to be doing Unit 7, Lesson 3 on factoring polynomials. Before we begin, let me remind you that you can find the worksheet and a homework assignment that go along with this video by clicking on the video's description or by visiting our website at www.emathinstruction.com. As well, don't forget about the QR codes at the top of every sheet. Scan those with your smartphone or with a tablet, and you'll be brought right to the video that goes along with that lesson. All right, let's begin. Factoring is one of the most important gateway skills in all of algebra. And I've always been fascinated by the fact that the word factor really has two distinct meanings. So now we're going to feel like we're a little bit in an English class as we look at the two meanings of factor before we even get into it. All right, so let's take the first one. To factor means a verb. It means to rewrite an algebraic expression as an equivalent product. And I really want to emphasize that, this means something like if I take the number 15 and I rewrite it as 3 times 5, I have factored it, right? If I take the number 18 and I rewrite it as 2 times 9, I factored it. Or 3 times 6, I factored it. Or 2 times 3 times 3. I've completely factored it. I'm going to get rid of some of this so that I don't get in the way of the next one. All right? So all factoring is rewriting an expression. All right? It may have variables in it or it could be completely numerical, but rewriting an expression as an equivalent product. But there's also factor the noun, and that's an algebraic expression that is part of a larger factored expression. So in other words, if I said, hey, what is the number 3? The number 3 is a factor of the number 15. The number 5 is a factor of the number 15. The number 6 is a factor of 18, so is 9, so is 2, so is 3. Those are all factors of the number 18. I mean, even if I factor 18 as 1 times 18, then both 1 and 18 are factors of 18. All right? So all of those are factors. So it's interesting. Most of the time, the more important one is going to be the verb. You will know that you must factor something, all right, to break it into a product. But sometimes you'll be asked which of the following is a factor of the following expression. Okay? So we're going to get work with both of those two meanings as we move on in the lesson today and in some of the lessons in the future. Okay, a very, very important skill. So I'm going to clear out that minor bit of text, and then we're going to jump into it, okay? All right, let's move on. So let's consider the expression 6x squared plus 15x. All right? Letter A says write the individual terms 6x squared and 15x as completely factored expressions. All right, I'll explain what that means, and then determine their greatest common factor. All right, so watch what I'm going to do. Right, I can break 6 up as 2 times 3, right? That's equivalent to 6. And then, of course, x squared is equivalent to x times x. There's nothing else I can break up here because both 2 and 3 are prime numbers. That's what a prime number is, a number that can't be factored anymore. All right, that's not exactly the definition of a prime number because then the number 1 would be prime and it's not, and that's a whole mess and I don't want to get into it. All right, so don't ask. Anyway, whatever. It's kind of actually cool why 1 isn't a prime, but not right now. Anyway, 6x squared is 2 times 3 times x times x. 15, well, that can be written as what? 3 times 5, right? And then times x. There's nothing else we can do. Now, what we want to do is determine their greatest common factor. Here, factor is being used in the noun sense. The noun sense. So I'm going to grab my blue, and let's find out what's common. That 3 is common, and that x is common. So their greatest common factor, known as the GCF, is 3x. That's not so bad. Now, what I'm going to do in letter B It says, using the distributive property, rewrite this binomial as a product, in other words, I'm going to factor, involving the GCF from A. So watch what I'm going to do. I'm going to write down 3x, and then I'm going to put down a parentheses. Now what I want to do is I want to put something in this parentheses so that when I multiply this all out, it's equivalent to 6x squared plus 15x. So what I want to think about is, well, what do I have to multiply 3 by to get 6? Well, not strangely enough, I have to multiply it by 2, and I have to multiply it by x. Plus, and that plus just comes from right here. Now I have to think about, what do I have to multiply 3x by to get 15x? Well, the only thing that's left over here is a 5. Let me go back to blue. So in other words, 6x squared plus 15x is the same as 3x times 2x plus 5. All right? That is factoring this, writing it as an equivalent product. Okay? Writing it as an equivalent product. Now to really hammer that home, let's take a look at C. It says evaluate both 6x squared plus 15x and the factored expression you wrote in B, that's this guy, for x equals 2. Let's do that first. So let's evaluate 6x squared plus 15x for x equals 2. All right, well, let's put the 2 in. Right? Now, of course, we have to square first, so that's going to be 4. Then we have to do the products. 6 times 4 is 24. 15 times 2 is 30. And then we add. And we get 64. We don't get 64, we get 54. All right. Now, let's evaluate 3x times 2x plus 5. Let's evaluate that one when x is equal to 2. Well, we'll get 3 times 2 times 2 times 2 plus 5. Sorry about all the parentheses here. I'm going to do this first. 2 times 2 is 4. All right, then we'll get 3 times 2. Now I'll do this addition. Of course, 4 plus 5 is 9. And now I have a three-way product. So I think I'll do this product first, which is 6. And then this, 6 times 9, and that gives me 54. And look at that. Look at that. They're equal, right? So what do you find? Well, what I find is they are equal. And what does that support about these two expressions? What's the word that we use? These two expressions are equivalent, right? So it supports the expressions are equivalent. It doesn't prove it, but it supports it. Expressions are equivalent. All right, and again, I don't want you to lose sight of that fact. Just like in the last lesson, we were multiplying out polynomials and getting equivalent expressions, equivalent polynomials. All right, now as we go in the reverse, and that's really what we're doing, we're reversing what we did yesterday, especially reversing the multiplication by a monomial. Now we're backing that out, right? And that's going to be much harder. As I tell my students, it is always more difficult to drive the car in reverse than it is to drive the car forward. And that's what factoring is, to go backwards from multiplying. Okay. Now, I'm sure at this point you might think to yourself, why would I care? And that would be a very understandable question. We will see a huge number of applications for factoring in the future in this course and in Algebra 2. So trust me when I say it's an important gateway skill. We're going to get a good start on it today, and then we're going to keep reinforcing it in future lessons, okay? So pause this video now and write down anything you might need to. All right, I'm going to clear out the text. Great. Let's keep going. So One of the things you're going to have to be able to do is identify these greatest common factors for monomials, okay? So in these problems, what we want to do is identify the greatest common factor for each one of these, and then write out each term as an extended product if necessary, okay? So what I'm going to do is I'm going to do a couple of these, writing out extended products, and then we'll start talking about ways that you can think about GCFs that don't require you to write them out. All right, but you can always write them out. So watch. Let me take 12x cubed. All right, what is 12x cubed? Well, the first thing I'm going to do is attack the number. Now, 12x cubed, well, that's 4 times 3 times x times x times x. But that 4 can be factored a little bit more, right? That's 2 times 2 times 3 times x times x times x. So that is 12x cubed completely factored. Let's take a look at 18x. Well, 18 is the same as 2 times 9, and then that x is just x. But 9 can be factored as 3 times 3. All right, let's change colors really quick to red. Let's take a look at what's common. I've got a 2 here, I've got a 2 here. Great. I've got a 3 here, I've got a 3 here. Great. Let's say I have an x and an x, and that's it. So what is my GCF? Well, my GCF is 2 times 3 times x, or just 6x. Now, what is the shortcut, so to speak? Well, first let's talk about the number, the 6. The 6 is the largest integer that divides evenly into both 12 and 18, right? It is their greatest common factor, also known as their greatest common divisor. GCF and GCD, there's really virtually no difference. Now, x cubed and x to the first, well, x cubed has an x to the first in it, right? It's x to the first times x to the first times x to the first. So x to the first is the biggest thing that's common to both of them, all right? So let's write out the extended products again in B, okay? And then see if we can use the trick, or to review the trick or the shortcut, what have you. All right, let's take a look at 5x to the fourth. Well, 5 is already a prime number, so there's really nothing we can do with that. All we can really do is write it like this: 5 times x times x times x times x. Right? On the other hand, 25x squared, well, that's going to be 5 times 5 times x times x. And again, let's use red and underline what's common. Common 5, but not two 5s. X, 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 and x. So the GCF is going to be that common 5 and then 2 x's. So 5x squared. Now again, how can we do this a little bit quicker? Well, we can look at this 5 and we can look at this 25, and the largest number that divides nicely into both of them is 5. Then we can look at x to the fourth and x squared and say, well, the smallest power that is sitting inside of both of them, or I'm sorry, the largest power sitting inside of both of them that's common is x squared. Right? X squared doesn't have an x cubed. It doesn't have an x to the fourth in it, right? But they certainly have more than just x to the first. They both have an x squared sitting there. So the GCF is 5x squared. All right. Here's what I'd like you to do. I'd like you to pause the video now. Write out letter C in both extended product form, and then we'll also go over it in the shortcut form. And then we'll probably just utilize the shortcut from then on out, okay? But pause the video now and see if you can figure out the greatest common factor of those two terms. It's a little bit challenging because it has both x and y in it, but I think you can do it. All right, let's go through it. Let me get back to blue. All right, 21x squared y to the fifth. Well, 21 is 3 times 7, those are both prime, times x, times 1, 2, 3, 4, 5. Oh boy, now I got y to the 7th coming up. Anyway, now we have 14xy to the 7th. 14 is 2 times 7 times just 1x, right, x to the first, times 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Great, got it. All right, back to red. There's a common 7, a common x, 1, 2, 3, 4, 5. I know I probably should have put dots there, but that's okay. Just looks kind of funny. So 7xy to the 5th is my GCF. Now, let's talk about that shortcut, right? We look at 21, we look at 14, and we come up with the largest number that divides into both of them nicely. That's 7. Then we look at x squared and x to the first. The largest power that is common to both is x to the first. Then we look at y to the 5th and y to the 7th, and the largest power that's common to both is y to the 5th. So 7xy to the 5th. Now let's try to use the shortcut a little bit more quickly. Let's look at these three terms. 24x cubed, 16x squared, and 8x. The largest number that goes into all three of those is 8. Then I look at x cubed, x squared, x to the first. Now remember, it's got to be common. The biggest thing that's common to all of them is simply an x to the first. So there's my GCF. Now at this point, a lot of students complain to me and say, man, that was just so much easier than writing it all out. I don't disagree. That's why shortcuts are often created. But at its fundamental essence, you can always figure out a GCF if things become very complicated by doing that complete factoring and then just pulling out those common factors one by one. Let's take a look at letter E. Actually, letter E is a relatively simple one. What I'd like you to do is pause the video now and take a shot at that. You can write out the extended product, or you can go right for the shortcut method. Either way, try to find the GCF. Pause the video now. All right, let's go through it. So we're looking at 20, 12, and 28. In my mind, it's a little bit ironic. I think the numbers are maybe the hardest part of this. We're looking for the largest number that divides into each one of these. And it's not a very large number. It's 4, right? 4 goes into 25 times. 4 goes into 12 3 times. Don't worry about the negative. And 4 goes into 28 7 times. All right? That's the largest number that goes into each one. Then I have an x cubed, an x squared, and an x to the first. So the GCF is just 4x, right? The largest value of x that's included in each one of them is just x to the first. This has no x squared in it. All right, letter F looks absolutely terrible. Pause the video again and take each one in terms, each one in its own turn. The numbers, then the x's, then the y's. But pause the video now and take a shot at finding the GCF. All right, let's go through it. So we're looking for the largest number that divides into 18, 45, and 90. That happens to be 9. 9 goes into 18 twice, 45 5 times, and 90 10 times. Then I look at this, x squared, x to the first. The biggest thing that's common to all of them is x to the first. Y squared, y to the first, y squared. The largest is y to the first. And there's our GCF. All right. Sometimes you'll be asked that simple of a question. I don't mean to imply that it's easy. I'm just saying that simple being that here's a bunch of terms. What's the GCF of the terms? All right. So what I'd like you to do, pause the video now and copy down anything you need to. Think about this page before we move on. Okay, I'm going to clear out the text and then we're going to move on. Let's do it. So now we're going to really go back to the first thing that we did, and we're going to start to write each polynomial below as a factored expression involving the greatest common factor of the polynomial. All right, so watch how we're going to do this. Let's take a look at 6x squared and 10x and identify its GCF, right? I look at 6 and 10. The largest number that divides into both of them is 2, right? Then I look at x squared and x to the first, and the largest thing they have in common is x to the first. So I write that down. That's their GCF. The GCF is 2x. And I throw down a little parentheses. Okay, now I ask myself, what do I have to multiply 2 by to get 6? And that's 3. What do I have to multiply x by to get x squared? That's going to be x. The plus comes along for a ride. What do I have to multiply 2 by to get 10? Well, that's 5. Now it would be tempting maybe to write down another x, but x times x would be x squared, not x to the first. So that's absolutely it. Now, how do you know you're right? Because if you multiplied this back out, you would get 6x squared plus 10x. That's how you'll always know whether you're right or wrong with factoring. If you multiply it back out, does it give you the right answer? Now, I do want to emphasize, though, that this is our final answer. We are undoing the multiplication. What we don't want to do is undo the multiplication and then redo it. Okay? So here's what I'd like you to do. Pause the video right now, take a couple minutes, and do problems B and C. All right, let's go through B and C. B might be a little bit tricky for some, because when I look at for the GCF is simply numerical. It's just 3, right? Because this doesn't have an x on it. So I pull the 3 out, and I ask myself, what do I have to multiply 3 by to get 3 times x? And that'll be x. Minus, what do I have to multiply 3 by to get 24? And that's 8. So that's it. 3 times x minus 8. Let's take a look at C. Okay, here, a little more complicated. I've got the 10 and the 15. There's a 5 that divides into both of them. X squared and x to the first, that'll just be an x to the first. What do I have to multiply 5 by to get 10? That's 2. What do I have to multiply x by to get x squared? That's x to the first. The minus comes along for the ride. What do I have to multiply 5 by to get 15? That's 3, and I already have the x. So there it is. Let's do one that's a little bit more complicated, or at least it looks like it is. A nice little trinomial here, right? So I look at the 4, the 8, and the 24. The largest number that goes into each one of those is 4. Now, there is no variable I can pull out because the 24 doesn't have an x attached to it. So the GCF is just 4. Not very much, but that's going to be actually quite common where we just have a numerical GCF that's similar to number 3. What do I have to multiply 4 by to get 4x squared? Well, by definition, x squared. What do I have to multiply 4 by to get 8? Well, 2, but I also need this x, otherwise I'll never get that 8x. And then what do I have to multiply 4 by to get 24? That's going to be 6. And again, the check ultimately is, if you multiplied it back out using the distributive property, would you get 4x squared plus 8x plus 24? And the answer is yes. All right. Pause the video, try letter E and F on your own, okay? All right, let's go through them. I look at the 6, the 8, and the 2, and there's a GCF of 2. I look at x cubed, x to the second, x to the first, and there's a GCF of x to the first. 2 times what gives me 6? Well, that's 3. What do I have to multiply x by to get x cubed? That's going to be x squared, right? X times x squared, add the exponents, gives me x cubed. Minus comes along for the ride. 2 times what gives me 8? That would be 4. What do I have to multiply x by to get x squared? That'll be x to the first. Now this last piece is a little bit tricky for some students. What would I have to multiply 2 by to get 2? Well, I'd have to multiply it by 1. And the x also comes along for the ride, right? So 2x times 1 would be 2x. Ultimately, you should always do a little mental check and see if the distribution works out to give you what you started with. Take a look at letter F. 10 and 35. Biggest integer that goes into both is 5. X cubed and x squared. Oh, I can get an x squared out of that, right? What do I have to multiply 5 by to get 10? That's 2. What do I have to multiply x squared by to get x cubed? That's x to the first, minus 5 times what gives me 35, 7, and the x squared is already there. All right. So, how about this now? Hopefully you've got the idea. Pause the video and work through the last 3 problems on your own, and then we'll go through them. All right, let's go through. Letter G, 10, 40, 50. I can get a 10 out of there, but because the 50 has no x term associated with it, or no x variable associated with it, the 10 is the best I'm going to do. That's going to make my life pretty easy, right? What do I have to multiply 10 by to get 10x squared? Well, x squared. What do I have to multiply 10 by to get 40? Well, that'll be 4, but the x has to be there as well. What do I have to multiply 10 by to get 50? Well, that's just 5. So 10 times x squared minus 4x minus 5. Let's take a look at this one. We've got 8 and 2. Let's pull a 2 out. X to the fourth, x squared. That will be x squared. Right? What do I have to multiply 2 by to get 8? 4. What do I have to multiply x squared by to get x to the fourth? That will be x squared. What do I have to multiply 2 by to get 2? Well, that's 1. What do I have to multiply x squared by x squared to get? Or so what do I have to multiply x squared by to get x squared? Well, 1. And that's it. All right, let's do I. We've got 8, 24, and 32. 8 divides nicely into all of them. X cubed, x squared, x to the first. We can get an x to the first out of there. All right, what do we have to multiply 8 by to get 8? That's just 1, so I'm not going to write it down. What do I have to multiply x by to get x cubed? That's x squared. 8 times what gives me 24? That'll be 3. X times what gives me x squared? X to the first. Minus. What do I have to multiply 8 by to get 32? That's 4. And the x just comes along for the ride. All right. Wow, that's a big page of GCF factoring, but it's important. It's the first type of factoring that we'll always look for. There's quite a few different types of factoring. There's 4 major types. You're going to only learn 3 in this course. There's 4 major types of factoring, and GCF is the first one we look at. In the next problem, we're actually going to look at a more complicated GCF scenario, but one that you've seen before. So pause the video now and write down anything you need to. All right, I'm clearing it out. Let's go on and do the last problem. Now, sometimes you want to be able to see the structure of an expression and be able to factor things out that are a little bit more complicated, right? So take a look at exercise 4. It says, rewrite each of the following expressions as the product of 2 binomials by factoring out a common binomial factor. This probably is going to actually be easier than some of the other problems. Let's take a look at letter A. All right, look at this term and look at this term. And yeah, I'm calling those terms because they are separated by an addition. Now, what's common to both, and this is probably pretty obvious, is this x plus 5. So that is their GCF, if you will, or at least it's a CF. I can pull out an x plus 5. Let me do that. All right, now if this feels like we've done it before, but a long time ago, absolutely. We actually did it in Unit 1, which I realize is a long time ago. But what did we multiply x plus 5 by? Well, we multiplied it by x minus 1. Plus, where did that plus come from? It's right here. And then we multiplied x plus 5 by 2x minus 3. Now notice, and this is very important, that this is addition. Right? And addition has all these nice properties, like it's associative, it's commutative, but because it's associative, what that means is that I don't really need these parentheses here, 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 and here. I don't really need those. Because that addition is associative, I can rewrite it like this. Then I can use a little commutative property and swing it around so I have x plus 2x plus negative 1 plus negative 3. So I'm turning everything into addition so I can rearrange it using the commutative property. I'm doing nothing with this x plus 5. Whoops, that should be a 2x. x plus 2x is 3x, negative 1 plus negative 3 is negative 4, and look at that. I now have this as the product of two binomials. Okay. Now letter B is amazingly more fraught with error, or with the possibility of error. All right, and let's take a look at why. Normally I'd say, hey, pause the video now and take a shot at it. All right, but there's something here that's particularly tricky. Now the first part of the problem isn't, we see this common 2x minus 1, right? Same deal. We have 2x plus 7 minus x minus 3, right? So again, that 2x minus 1 is just going to hang out. But now it's a little bit more difficult. We can't just simply remove the parentheses. We actually have to distribute a multiplication by negative 1. In other words, we have to change subtraction really into addition of opposites. So I distribute that multiplication by negative 1. Negative 1 times x is negative x, and negative 1 times negative 3 is positive 3. At that point, though, it allows me to do what I did in the last problem. In other words, I can swing things around. Many of you will just choose to combine like terms at this point, and that's okay. I just really want to show that commutative property that we're using, right? And then this is really the associative property. I choose to combine these two, giving me a single positive x, right? Positive 2, negative 1 gives me positive 1. And then, of course, 7 plus 3 is positive 10. And there's the product of two binomials again, right? So GCFs don't have to just be monomials. A GCF could be a binomial. It could even be trinomials or things that are higher level. In this course, the biggest GCF I think we'll ever see will be a binomial. But it's kind of cool because you can pretty easily factor those out. All right, pause the video now. Think about what we just did, and then I'm going to clear out the screen. Okay, here we go. Let's finish up the lesson. All right, today we started learning one of the most important skills in all of algebra, and that's factoring. For years, factoring has been known as a gateway skill because there are many, many problems that will hinge on your understanding of factoring, both in this course and a lot more in Algebra 2. So it's a skill, kind of like addition, subtraction, multiplication, and division, that you need to become good at early on. We're going to work with it more in the next few lessons, so you will gain some fluency with it. For now, let me thank you for joining me for another Common Core Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.